Hello everyone, and welcome to Control Engineering and Control Theory tutorials. In these tutorials, we present real and applicable knowledge of control engineering and control theory. In this particular tutorial, we provide an introduction to Lyapunov stability analysis of dynamical systems, and we provide examples. But before I start, I would like to mention a few things. First of all, those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains graphs, equations, and all the explanations. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this video tutorial and this post, and I kindly ask you to press the like and subscribe buttons. Thank you very much. So let us first explain the main motivation for the Lyapunov stability analysis. Consider the following nonlinear dynamics. X dot is equal to f of x, where x is a state vector and f is a nonlinear vector function. Then, let x star equal to 0 be an equilibrium point of this system. Here, for simplicity, I assume that 0 is an equilibrium point. However, everything stated in this tutorial can be easily generalized to the case of non-zero equilibrium point. This can be achieved with a simple change of state space variables, and I will talk more about this in my next video tutorials. When analyzing the stability of a dynamical system, we want to provide answers to the following questions. Number 1. Is the equilibrium point x star is equal to 0 stable? Then, number 2. Is the equilibrium point x star is equal to 0 asymptotically stable? In the case of linear systems, these questions can easily be answered by computing the eigenvalues of the A matrix of the linear system. If this is our linear system description, shown over here, x dot is equal to ax, then we only need to compute the eigenvalues of the matrix A, and from the eigenvalue location in the complex S-plane, we can provide answers to these questions. For example, if the eigenvalues are located here and here, then the system is asymptotically stable. However, in the case of nonlinear systems, these questions are far from trivial, and in order to provide answers to these questions, we need to employ complex mathematics. There are at least two methods that can be used to answer these questions. The first method is the so-called Lyapunov's indirect method, that's also known as the Lyapunov's first method. The main idea of this approach is to linearize the dynamics of the nonlinear system around the equilibrium point and to investigate the stability of the linearized dynamics. If the linearized dynamics is asymptotically stable, then the equilibrium point of the nonlinear system is also asymptotically stable. On the other hand, if the linearized dynamics is not stable, then the equilibrium point of the nonlinear system is also not stable. I will explain the Lyapunov's indirect method in my future video tutorials. The second method that I will explain in this video tutorial is the Lyapunov's direct method. This method is also known as the Lyapunov's second method. This approach is based on finding a scalar function of a state that satisfies certain properties. Namely, this function has to be continuously differentiable and positive definite. If the first derivative of this function with respect to time is negative semi-definite along the state trajectories, then we can conclude that the equilibrium point is stable. On the other hand, if the first derivative along state trajectories is negative definite, then the equilibrium point is asymptotically stable. This tutorial is dedicated to the practical application of Lyapunov's direct method. And before reading this tutorial, it's a very good idea to revise the concept of positive and negative definite functions. These concepts are explained in my previous tutorial, which can be found over here. In this tutorial, you can learn what are positive and negative definite functions, and you can also relate positive and negative functions, positive and negative definite functions with quadratic forms and with matrices. And it's a very good idea to go over this tutorial before watching this video or reading this tutorial. Before we introduce examples, it's very important to state the Lyapunov's local stability theorem for an equilibrium point of a dynamical system. This theorem is stated in a number of standard textbooks on nonlinear systems, such as, for example, this book, Nonlinear System by Hassan Halil, and this is the edition I have from 1992. And the theorem is stated on the page 101. Then, another book that I like very much is The Applied Nonlinear Control by Jean-Jacques Slotin and Wei-Ping Li, and this is the edition I have from 1991. The theorem is stated on page 62. Here's the Lyapunov's local stability theorem, which is a reformulation from the first reference. We consider a dynamical system, x dot is equal to f of x. F is a nonlinear function of the state x. Let x star be an equilibrium point. That is, x star is a point for which f of x star is equal to 0. Let us assume that we are able to find a continuously differentiable scalar function of the state vector argument, and this function is usually denoted by v of x, and this function is defined on a neighborhood set D of our equilibrium point. So graphically, you can imagine a point x, that is equilibrium point, of the system, and some neighborhood, denoted by D, around this equilibrium point. And in this case, this neighborhood is a simple ball in Rn. Now, if we can find this function v of x that satisfies these two conditions, then we can make very strong conclusions about the stability of this equilibrium point. The first condition is that this function v of x needs to be locally positive definite in D. That is, v of 0 should be 0 and v of x should be larger than 0 on this domain, except, of course, at the equilibrium point x star is equal to 0. To graphically illustrate a positive definite function, we can take a simple quadratic function and one-dimensional case. So if this is one-dimensional state space vector, this function is positive definite. This is v of x. And this function is globally positive definite since it's always larger than 0 except at x is equal to 0, where v of 0 becomes 0. Okay, so this is the first condition for v of x. The second condition is that the first time derivative of v of x should be locally negative semi-definite in the domain along any state trajectory of the system. That is, if we compute the first derivative of v along the trajectories of the system, then this first derivative should not be positive, should be either negative or equal to 0 for all x in D, that is for all x that belong to the state trajectory of the system. If these two conditions are satisfied, then x star is stable. In addition, if the first time derivative of v of x is locally negative definite in the domain, that is, if v dot of x is always smaller than 0, then this function is asymptotically stable. Of course, when I say this, I don't mean that this condition should be satisfied at x star is equal to 0. So keep in mind this thing. So if this condition is satisfied, then the equilibrium point is actually asymptotically stable. Now, let us explain the physical intuition for this theorem. Again, let us consider a Lyapunov function that looks like this. And let us consider a simple system that's basically this system. The question is this system stable or not? Here, I need to add that the function that satisfies these two conditions is called the Lyapunov function. When analyzing the stability of dynamical systems, we have a freedom of choice. We can freely select v of x. However, this v of x needs to satisfy the condition 1 and condition 2. That is, it has to be 1, positive definite in some domain around the equilibrium point, and number 2, the first time derivative of this function along the state trajectories should be either negative semi-definite or negative definite in domain around the equilibrium point. If these two conditions are met, then this function is actually our Lyapunov function. In the general case, that is, in the case of a very complex dynamics, f of x, it's very challenging to find the Lyapunov function for the system. Usually, good guesses are energy of the system, for example, because we know that conservative systems always conserve the energy, or dissipative systems always dissipate energy. And consequently, the Lyapunov function that has a form of energy is a good candidate function. And notice here that I said candidate because a function becomes the actual Lyapunov function only if it satisfies 1 and 2. Here's our Lyapunov function, and here's our example. X dot is equal to minus x. This is a first order differential equation that we can solve very easily. So let's solve this differential equation. From this equation, we obtain that dx over dt is minus x, or dx over x is equal to minus dt. Let us integrate this equation, and as the result we have that ln of x is equal to minus d plus some constant. And this constant should be determined from the initial condition. Before we do that, let's transform this equation. We can write x is equal to e to the power minus d plus c. Next, let us assume that at the initial condition x0, the system is at x0. Graphically, we can, for example, pick this initial condition and let this be x0. By substituting this initial condition in our solution, we obtain that x of 0 is equal to e to the power c. And consequently, the solution can be written like this. X is equal to e to the minus t times e to the power c. That is, our solution is x is equal to x0 times e to the minus t. And over here, I will repeat this solution for clarity. So what's happening over here? In this case, as the time goes by, that is, as t increases, the right-hand side of this equation will decrease. That is, we will approach 0. And notice over here that 0 is actually the equilibrium point. On the other hand, if we start from this side, that is, if the initial condition is negative, let's call this initial condition x0 tilde, then what happens over time? Again, the right-hand side of the solution decreases in absolute value. That is, we can see that x will go in this direction and it will asymptotically approach 0. However, it will never approach 0 in finite time. And obviously this equilibrium point is asymptotically stable. Let's go back to the Lyapunov stability analysis. In the Lyapunov stability analysis, we don't explicitly solve this equation. Instead, we compute the first derivative of v of x and see how this derivative behaves along the state trajectories. So let's do that. Let's compute the first derivative of v of x along the state trajectories. V of x is x squared, since I selected my Lyapunov function to be quadratic function. Let us compute the first derivative of x. The first derivative is 2 times x times x dot. Here we are using the chain rule to compute the first derivative. This is because we assume that x is actually a function of time. And keep in mind this thing. This is very important. Consequently, if we want to compute the derivative of any expression that involves x, we first need to treat x as a constant variable. That is, we compute the derivative assuming that it doesn't depend on time, and that's why you obtain here 2 times x, and then we assume that actually x depends on time, and then we need to differentiate x with respect to time, and that's the explanation. So this is the first derivative, and this is the general form of the first derivative. Then we want to compute the first derivative along the state trajectories. So we basically substitute our state equation in this equation. And as the result, we obtain this equation. 2x times minus x. And as the result, we obtain minus x squared. Let us analyze this expression. Obviously, this derivative is always negative except at the equilibrium point. And this means that according to the Lyapunov stability theorem, the equilibrium point is asymptotically stable. Next, we give the third interpretation of the Lyapunov stability theorem, and this interpretation is very intuitive. Previously, we have shown that if we start from a certain initial condition, our state trajectories will approach the equilibrium point. On the other hand, if we start from this side, the state trajectories will again approach the equilibrium point. Let's go back to the Lyapunov stability theorem. The Lyapunov stability theorem states that the first time derivative of v of x is locally negative semi-definite or negative definite in D along any state trajectory. This means that we need to look into the behavior of our Lyapunov function along the state trajectories. So let's say that we start from here, right? From this state x. This value over here is v of x. So let's see what happens with v of x over time. Since we follow this point and this point goes left, this means that this ball on this hill will roll down. For example, if the state is here, the ball will be here. So you can see the state in this plane or in this line as the projection of the ball rolling down this hill. And obviously, if let's say this is the initial state, let's call it x0, and this is some state, let's call it x tilde, we can see that vx0 is larger than vx tilde. This actually means that v of x0 minus vx tilde is larger than 0, or on the other hand we have that vx tilde minus v of x0 is smaller than 0. Then let us divide this equation by delta t. And then let's take the limit value when delta t goes to 0 of this expression. This expression is nothing less than the definition of the first derivative of v with respect to time along the state trajectories. And this first derivative is smaller than 0, since our function v of x decreases. And this is the intuitive explanation of the Lyapunov stability theorem. We'll look at what's happening with this function v of x along the state trajectories. If this function decreases over time, then we know that our equilibrium point is asymptotically stable. However, if it remains constant or sometimes decreases, then we can conclude that the equilibrium point is stable. Next, let us analyze the stability of a more complex system. We consider a pendulum system shown in this figure. Theta is the rotational angle, L is the length of the rod. We assume that the rod doesn't have mass and it's rigid. M is the mass of the ball, G is the gravitational acceleration constant, and F is the external force, and this is the external input. What is interesting over here and what should be kept in mind is that when analyzing the stability of a system, we always assume that the external forces and external actions affecting the system are 0. And we only analyze the stability with respect to the initial conditions. So keep in mind this very important fact. In my previous tutorial, which can be found over here, I derived an equation of motion describing the dynamics of the system, and the dynamics is shown over here. Because we neglect the force F when analyzing the stability, we assume that F is equal to 0 and we obtain this equation. Next, we introduce state space variables. x1 is theta, x2 is theta dot, and here's the state space model. Next, let us simulate the state space trajectories of the system. In my previous tutorial, which can be found here, I explained how to write a MATLAB code that will generate you these type of graphs. These type of graphs are actually phase portraits of dynamical systems. They show you how the system behaves from a certain initial condition. For example, you have here an asymptotically stable system, and if you place an initial state over here, the system will evolve like this. These arrows are actually the directions of movement of your state trajectory. The MATLAB code is given over here, and you can easily modify this MATLAB code to simulate the state trajectory of the pendulum. And here's the simulation. Here is our initial condition. I assume that x0, 1, that is x1, 0 is pi over 6, and x2, 0 is 0. So I'm assuming that I'm starting, for example, from this position. So I place the pendulum in this position and I release the pendulum. The pendulum will oscillate like this with a constant amplitude. And that's exactly what you can see over here. x1 is theta and x2 is theta dot, that is the angular velocity. As can be observed from this figure and from this arrow, the equilibrium point is stable. However, it is not asymptotically stable. Let us now construct a Lyapunov function that will be used to formally prove that the equilibrium point is asymptotically stable. For that purpose, let us consider this graph over here. Over here, you can see the velocity of the ball, and it's always tangent to the trajectory. The trajectory is a part of the circle. Next, let us select a Lyapunov function for this system. Note that when investigate the stability of the system, we have a freedom of choice. That is, we can freely select our Lyapunov function candidate. I say candidate because not every function is actually Lyapunov function. Lyapunov function is the function that satisfies the conditions of this theorem. That is, it has to be locally positive definite in a domain around the equilibrium point, and the first derivative of Lyapunov function should be either negative, semi-definite, or negative definite. And if these two conditions are met, then the function is actually the Lyapunov function. I mentioned this previously, but I will repeat this again since this is a very important thing. A good initial choice of the Lyapunov function is the total energy of the system. This is because if the system is asymptotically stable, then the energy of the system should decrease over time. Or if the system is stable, then the total energy is either constant or bounded. That is, it's not increasing. Consequently, let us define the total energy of the system, and let us select the Lyapunov function candidate as the total energy. The total energy is a sum of potential and kinetic energy. The kinetic energy of the ball is 1 square mass of the ball times velocity square plus mgh, and mgh is the potential energy of the ball measured from this reference plane. Obviously, the velocity is the length of the rod times the angular velocity theta dot. From this expression, we obtain that the kinetic energy is 1/2 mass times L squared times theta dot square. On the other hand, let us calculate the potential energy. Potential energy is mass times gravitational acceleration constant times this height over here. The vertical distance between the center of the ball and the reference plane. From this graph, we see that this expression can be written like this. H is nothing less than L minus L cosinus theta. By substituting this expression in our Lyapunov function candidate, we obtain the expression given by the equation 8. Now, in order for this function to be the Lyapunov's function, two conditions should be met. First of all, this function should be positive definite and v of 0 should be 0. Then, in order for this function to be the Lyapunov function, we need an additional condition, and this additional condition is that v dot of x is smaller or equal to 0 for the state trajectories. Let's first investigate the positive definiteness. Since this term at 0 is equal to 1, when x1 is 0, this whole part will become 0. And the kinetic energy is obviously 0 for x2 is equal to 0, so it's obvious that v of 0 is 0. Perfect. Then, let us investigate, is this function always larger than 0? Obviously, the kinetic energy is always positive, except for x2 is equal to 0. Then, the potential energy is always positive for x1 not equal to s pi, where s is 0, plus minus 2, plus minus 4. Consequently, we conclude that also potential energy is positive except at the points 0, plus minus 2, plus minus 4 multiplying pi. Consequently, v of x is always positive over this domain. So x1 is from minus 2 pi to 2 pi, and x2 is from minus infinity to plus infinity. Next, let us compute the derivative of v of x along the state trajectories. Again, here we assume that x1 and x2 are actually functions of time. And keep in mind this when computing the first derivative. So let's see what happens. Over here, what do I have? And for clarity, I will write again my v of x function. The v of x function is 1/2 mass L square x2 square plus, let's see what is exactly from the original expression. And for that, I need to do something like this, and I will write it over here. So the second part is mgl 1 minus cosinus of x1. Perfect. Let me just double check. 1/2 mass L square x2 square mgl 1 minus cosinus x1. Perfect. Let's go back. And let's compute the first derivative. Let's see what happens. What is v dot? V dot is obviously 1/2 mass times L square, and mass and L square are constant. Let's see what happens over here. We know that x2 is actually a function of time. Consequently, we need to apply the chain rule. We have 2x2, and then since x2 is actually a function of another variable, we need x2 dot. Okay? Similarly, over here we have mgl. Since derivative of mgl times 1 is equal to 0, we don't have anything. And then over here we have derivative of cosinus of x1. Actually, we have a minus sign over here. So derivative of cosinus is minus sinus x1 multiplying x1 dot, since we know that x1 is actually a function of time. And as the result, we obtain this expression over here. Next, let's go back to our Lyapunov function. And let's read carefully the Lyapunov function. Here it's written that first time derivative of v of x is locally negative semi-indefinite in d along any state trajectory. This means that we need to couple our first derivative of the Lyapunov candidate function with our model. And here is our model. So instead of x1 dot and x2 dot, in this equation, we use the expression from our dynamics. So instead of x1 dot, I will write here x2. And instead of x2 dot, I will write minus g over L sinus x1. And after substitution, we obtain this expression. And we can conclude that v dot of x is equal to 0. Consequently, according to the Lyapunov local stability theorem, the equilibrium point x star is stable. This is because v dot of x is equal to 0. The physical interpretation of this result is that the energy stays constant along the trajectories of the system. This is actually the law of energy conservation. That is, the potential energy transforms into the kinetic energy and vice versa. However, the total energy in the system remains constant. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.